Good morning, everyone. Welcome to this session. We are on Wednesday. Happy Wednesday for everyone on April 22nd. And we are going to be starting a brand new topic. And on Monday, we wrapped up a discussion we started a week before on reducibility. And as I mentioned then, this would transition us to the last portion of the course, much like an introduction to a new thing, but it's not going to be something that we need to spend a whole lot of time in, but there are some interesting things that I would like you to have an idea about and be introduced to. I hope everybody's doing well and going strong, and only 1 week left in terms of lectures, and I'm hoping that all your classes are going well and you are staying safe and healthy and you're doing well in what you are taking. The homework that is due on Friday, hopefully it's going fine. We spent some time talking about it last time. Every time when I have a slide like this, I try to kind of find, and the book had done a good job, a one-word title or a two-word title. And so I thought a little bit about this one and I kind of got to the point very quickly. And so it says time complexity. James noticed last time when we had this mapping reducibility, and it struck a chord with him on what map reduce, and some of you may know that. And so there are things that would invoke a certain thing whenever we see words and titles like that. And so I'm going to allow people to come in now, and we are going to have a warm-up question quickly, and there will only be one. And I remember at some point, a few weeks ago, I think it was, I asked you about reading and the kind of things that you like in terms of favorite genre when it is about reading and literature. And so there were different categories. And if you don't remember exactly what I posted afterwards, it turned out that science fiction was the thing that most of you liked the most. And so there were 5 or so categories that you had to choose from. And so that seemed to be the highest one. But there are different kinds of readings you would do. You would read a newspaper, and then maybe you have some favorite places to go, some columns that you like to read, or the sport or the weather or business or things like that. Or there could be a radio, talk show that you hear, or TV that you show, and you hear this word analysis. And my question, my warm-up question for the day is, and I've given a little bit of a context. You're reading something or a show or a TV or a radio program, and the word analysis is used, and it's used frequently. When you hear the word analysis, what comes to mind? You could do a 1-word, a 2-word, and maybe a little bit longer, a phrase. But think about what analysis would invoke to you. What would it mean? What comes to mind when you hear the word analysis? Warm-up question for the day. What comes to mind when you hear analysis? And I have given you a little bit of context to go around for it. And so keep that in mind and keep participating. And I remember when I asked it what words would come to you when you hear the word philosophy. It was one time I asked you because there was something around computability that got some kind of connections with philosophy, especially when we talked about diagonalization. So there were some very interesting answers. So give it some thought and tell me what comes to mind when you hear the word analysis. For the benefit of those who joined late, and I don't want to be asked later on, I'm going to just type up the warm-up question for the day and come back and start getting started with what we want to do today. So when you hear the word analysis, what comes to mind? Radio hostess would say that stay, if you hear NPR, they would say stay for us. There will be some analysis or some other things when reading, and so some writings would be called opinion and others would be called something else. And there are some times when people would use that word analysis. So go ahead, tell me what comes to your mind when you hear the word analysis. And we are going to get started with what I would like to get done today. So if we take a look back at what we did in the course, there were 2 parts. The first part had to do with automata and language. And the kind of things we discussed there was regular language and context-free language. In fact, there was a chapter on each. And these were the headings of the chapters in the book, nicely, aptly described. The second part of the course was about computability theory. And we started off with the Church-Turing thesis. We looked at lots of different kinds of Turing machines, variations, but the basic definition for it. And then we made our way we did it, all the things that we need to have a definition for an algorithm. And then we spent a chapter on decidability. Language and most of the problems that we look at in this course are formulated in the form of language and memberships and things like that. And so there was this question of, when is it a problem? We call it decidable. When can we have a Turing machine that decides it? And so that was a portion we spent some time on, decidability. And then came reducibility, when we reduce one problem to another. And we saw several variations of this. Because there were problems that were undecidable, we needed this mechanism for having to show undecidability by having to reduce from a problem that's known to be undecidable to a problem that we are considering. And so that was our tool. And so if we put all this together, they happen to be chapter 2, chapter 3, or chapter 1, chapter 2, chapter 3, chapter 4, chapter 5. That's how they were. These 5 chapters would constitute, for the most part, what the bulk of this course is, and we completed that. And so we have come now to a point where the book would go to a third part, and that's called complexity theory, as opposed to computability theory. This is not a big portion in our course. In fact, you would be introduced to complexity theory in courses that you would take later on in algorithms class, for example, in computer science, or if you take a graduate level class, you would take complexity theory in a big way there. But we are in a position to appreciate what it is and get introduced to it. And so that is the goal for today. And we will have today's lecture and tomorrow's Friday's lecture having an introduction to complexity theory, which is part 3 in the book. If you want to see, for example, what homework 8 would have, there may be just some introductory type of problems, 1 or 2 that I would throw in. Otherwise, the subject, the whole point of this course is around parts 1 and 2, which we have completed. This one is also a nice introduction into some things that you might encounter, even though they don't come up in the form of a course or something like that, but you encounter them in your computer science courses or other courses. And so to be able to do analysis, that's the word, and we'll get to there, would be important. And in that sense, this is also a nice introduction, and it's a lot of fun. And so this is what we will be doing. And the portion, the third one, when we say complexity theory, deals with the following thing. So when we looked at this decidability question, when we introduced Turing machines, we convinced ourselves that there are problems that are decidable and there are problems that are undecidable. When problems are decidable, it's not the end of the world. We could have problems that are theoretically by the end of the world. I don't mean it in a negative way. I don't mean there isn't anything else to do. We know now it's decidable, and so we just throw our hands off and there is nothing more. It's not like that, is what I mean. And so when problems are computationally solvable, and that, in other words, decidable, what else is there to do? Because they may, in some cases, for all practical purposes, just be unsolvable because they talk a lot of resources. And so we need to investigate resources that are required when problems are computationally solvable. For computational problems, we want to find out what resources we need. As computer scientists, and sometimes it has got a little bit, I would say, with physics or how we view the world, time and space are the resources we have. And so time, and when it comes to computers, we would call it memory. That's what space is. And so these are predominantly the ones that we care about, and we look at into seeing how much of that resource is used. But sometimes we may have other resources. They come rarely. And this is a place where people like you, who would probably redefine what complexity theory, computability theory would be in the future, where maybe something other than Turing machines would come. There may be other resources that might be important. But even now, we see sometimes there are other resources than time and memory that we can have in our computational models. I don't want to get too much into what those others are, but have time, memory, and some other things, whatever it might be. It might be some kind of external device, some kind of an addendum we have, or some kind of communication, some kind of bandwidth, this sort of things that are included in a computational model might be subjects for investigation, how much of a resource of those types we have used, but primarily it will be time and memory. And the book, when it deals with complexity theory, takes time and space separately, and it'll be a chapter on its own, but we will, because our goal is now introductory, we will, among the three choices we have here, or really two choices we have here, time and memory, we will focus on time. And that's why this discussion today is headed time complexity, and what we would be doing also would revolve around it on Friday. If I don't get to finish everything I want to do on Friday, we will slip over to some of those things to next week. Just 5-10 minutes of that week will be borrowed rather than reviewing for the entire semester in a way. And so time complexity now means we are going to deal with problems that are decidable, computationally solvable, and we are going to analyze them in terms of how much is needed to solve that problem time-wise. We also could have done, and we do usually in a theory like this, there are requirements in terms of space, but we leave that out. So it's time. So how is time measured? And how do we classify problems according to the amount of time needed is the subject matter of time complexity theory, or time complexity analysis, you could say. But time complexity will be a phrase to use that, and that is what we will be doing. Okay, so how do we measure complexity? We're going to start with an example, and an example that is familiar. You remember this language. The only thing is probably we called it B the first time we saw it. And I'm 100% sure you remember this one. We've come across it so very many times. And so we have, this is a language, a sequence of zeros followed by a sequence of ones, they're of equal number. You might be curious now why all of a sudden I've changed it to K. Not me, the book does. And we have a reason. And we have, computer science is interesting because some of these notations that we use, some of these letters have got special meanings, and we never want to get them mixed up with other things. And so we reserve them for a special purpose. And time complexity, or complexity analysis in general, is fond of a couple of letters. And I will introduce one of those big letters later on. So a clue for why we have changed this language that we are familiar with, we know from before, and now it has got a K instead of whatever that other was, has got a reason. So we've got this language, and we want to see how much time does a single tape Turing machine need to decide A. You might now wonder what I am trying to do. So first of all, this is a decidable language. Otherwise, I wouldn't have cared to analyze it further. It wouldn't have been a subject for today. And the other thing is I have talked about the Turing machine, because that is our way of getting into both computability and complexity theory. So Turing machines are our models. I am sorry if finite DFAs and NFAs were your favorites when I asked you in the last lecture. All I asked was what was your favorite. It could be their look, nothing else, or how easy they were, and they are easy. And so Turing machines are the ones, not to change your minds to make your favorite, but we have advocated for them for what they do. So Turing machines, algorithms, you could think of them as synonyms for all practical purposes, right? So we are going to now to say how much time does a single tape Turing machine need to decide it. So I am now into the business of doing how much time does it take. I'm going to measure that. That's where I am. But the qualifier I have here is intentional. I've said single tape. Usually we don't talk about how many tapes there are in a Turing machine, because we have established that these things don't add power. Remember that. So those things don't add power doesn't mean they're the same. And sometimes you might have asked me when there was a problem, in one of the homeworks, can I use this type of Turing machine to show it instead of this one? Because it's of course, they will be convenient. There will be shorter steps to describe it and things like that. But the addition, the variations we have added to Turing machines do not change fundamentally what the Turing machine as a class could recognize as a language. So the language, they recognize the same thing. They're not going to add another language, another class, another bigger thing, and therefore they're equivalent in that sense. But I wanted to qualify now, and I have a reason for doing that. It will be clear in a moment. Okay, so how much time does a single tape Turing machine need to decide A? I'm going to throw the Turing machine that we will be working with, and we will call it M1. Every time you see me do this or the book does this, you can suspect now, okay, he's going to come up with another one later on. That's why he's calling it M1, and that will be true. We will see another one. This one is, you've seen this Turing machine description, except that it is more like an implementation level type of description now before. And so the goal is not now to convince you for a language that you already know, 0 to the k, 1 to the k. When k is greater than or equal to 0, you know that it is decidable, and here is the Turing machine that decides it. My goal now is a different one. It is about going step by step and looking at these steps and trying to find out how much time does it take. We are going to measure complexity. And the way we do this is pretty rigorous, actually. We go in around each of these steps and try to see how many things are there, how many operations are there, then what would it cost? And so we've got this, and just so we get very quickly to it, this Turing machine has got this description. The first stage is to scan across the tape and reject if a 0 is found to the right of a 1, right? That will obviously not qualify to be a member in this class. Otherwise, if there is, or we go to the stage 2, and so we repeat, if both 0s and 1s remain on the tape, as long as there is thing to do, we scan across the tape, crossing of a single 0 and a single 1. That's where we're matching them up, right? And if 0s still remain, we are now, I just did step 3. And in step 4, if 0s still remain after all the o's have been, the 1s have been crossed off, or if a 1 still remains after all the 0s have been crossed off, we reject. Otherwise, if neither 0s nor 1s remain on the tape, accept. If this was homework 6 or 7 or whatever it was, when I would have said, give me a Turing machine and give me an implementation level detailed description for it, you would get a perfect score on this one. This will be what you would write. What we will do now is go through this and look at what the tape has done, what kind of things have happened to count or to measure how much time it took for this machine to do the job. And that is what time complexity would be and will be measuring. Okay, so for this purpose now, if I had asked you, you would have needed to know what the input is, how it is described, to be able to tell how many steps it has taken. For the purpose we are going to be, and this is called the running time of the machine, the Turing machine. We are going to assume that the input is given in some kind of description. And so we are not going to be too interested in exactly how it is done, but we have an encoding in some ways that measures how the input is given to us. And that name, we will give it a size. The size of that description is what is called n. And that is the term I was alluding to, that the parameter that's used to mean a special thing. Usually, when the context of time complexities and things when results are analyzed, and you probably have seen them before, if your textbooks have probably said that. N is the word that's used. So it's the input size. And it represents just simply the length of the input. And so the running time now, the way we measure, we're not going to take a clock and then see how much our code is running, or the Turing, we're not doing this on a computer at this point. We just have a Turing machine. So the way we measure time is not to set a clock and then wait and we get an answer and we take the time and we take the, no, we just do this analytically, right, while looking at it. And so we're going to have a function that will take this input and give me a number. And that function is f of n, we'll call it. And we do that with the maximum number of steps that the machine needs on an input length n. So there are different kinds of analysis one can do. You have the description of a Turing machine that is just given now that decides that language, and there may be some things that would make it go, certain kinds of input that may go it slightly faster, on another ones it could be slightly slower, and so on, right? What we would do, and there will be times when the numbers that are given here would be easy to decide, and so it doesn't take you very long, and the way the thing that he wanted to decide was specified, except for the very last thing, after all of the checks have been made, the cross-offs have been made, and so on. It was only at the very end that something wrong was discovered, and so the algorithm would decide. But if it early found out that this thing doesn't belong, it's not going to spend all that time. So there is different kinds of analysis that you would do. In computer science, we do something called worst case analysis, and that is the more common thing. If people do not tell you what they're doing worst case analysis. That means in the worst case, whatever the instance may be, this is how long it would take. And so you kind of give the running time in that sense. Another type of analysis would have been an average case analysis. Usually it's difficult to do an average case analysis. And so we'll work on something that is worst case, and that's why you see this Fn now being called the maximum number of steps that this machine uses on any input length of length n. And so we'll call that F function f of n is now called the running time of n. So when you see now how I am measuring time complexity, I'm not going to give you in seconds or hours or days or something, unit of time, but rather, given the input, I would express a function that will tell me how long it would take. So it will be a function of the input length. And it makes a lot of sense to talk about as a function of the input length, because the input is what the tape is doing. On its tape, it's going to manipulate it, doing, writing it there and moving things around. And, the tape is, so the input size matters, in other words. And so whatever it is that we would express will take as a function from a natural number to another natural number. And so the domain is the input's length, and the range, what this function is outputting, is the runtime, the running time of the algorithm. Okay, so that's how time complexity is measured. Another thing we do in computer science, and a very, very convenient thing, is what is called big O notation, or what the analysis we do is asymptotic. The reason for it is kind of similar to what I told you when we had that problem 2 in homework 7, where you got a little bit of a hint on, and I told you to bound. We actually do care about bounds. We do care about things that would be in an asymptotic nature. As things go, as n goes big and big and big, what is the feature that's the most dominant among the expression that you can give? And then you leave out things that are less important. So you focus on the one that's dominant, and you would not care about constants and things like that. And so the general grows how things are. So if somebody was going to show you on a slide and then how things are spreading these days, unfortunately, or whatever, the economy is growing, or the population size is growing in the world and so on. Usually what you want to get is a feel how fast it's growing, not necessarily exactly those numbers and things like that. And so sometimes the growth could be just linear, sometimes it could be more than that, sometimes it could be exponential, and that sort of understanding, higher level understanding, where lower terms are ignored and coefficients are ignored. That type of analysis is called asymptotic analysis, and we have a notation called big O, and the name comes very conveniently from the way it looks. There is an O right there, and it is big, and that's why it's called big O. And so we have, now this is a formal definition for a big O notation. I am almost sure that you've seen a definition of this kind somewhere else in your courses. If not, then you are seeing it for the first time now. So let f and g be functions. They're just functions. They from the natural numbers to real numbers. And we will call now f of n is equal to big O of g of n. And so look at these two functions, how they are related now. If there is a positive integer c and some constant and some no that exists, such that I can always bound this fn by a constant times gn. If I can do this, then f of n is less than g of n, is basically what it will be. So if you want to have a very convenient way of thinking about this one, think of that f of n is equal to order of g of n, just to mean that there is a bound on a function g that bounds fn. So f of n is less than or equal to g of n. I will tell you why I say equal to, but think of it that way. So f of n is less than or equal to c times g of n. When I can find a constant and some no, where this would be satisfied, then I can use this notation. F of n is order of g of n, of big O of n of n. Okay, when f of n is order of g of n, we say that gn is an upper bound for f of n, which is obvious from what I just said and how it is defined. Or more precisely, we say gn is asymptotic upper bound when we really, really want to spell it out. But it is an upper bound is what we mean. To emphasize that we are suppressing constant factors. So we are interested in worst case analysis. A way for us to measure time complexity is by looking at running time, which will only depend on the length of the input and nothing else. And we use big O notation because we suppress constants and lower terms and focus on the bigger terms only. Okay, here is an example. And because this is not so easy to type up on PowerPoint, I just had picked an example from the book. So don't get scared if this looks a little too much text to be written. And we'll just look at that example, and it's a nice, cute example. So you should be able to absorb as I describe it. So we've got a function. Now we are doing an example when if we were to express this function as order of something, what would that something be is what we are doing. So we'll call this function f1 of n, and it's fn cubed plus 2n squared plus 22n plus 6. And out of this, it has got 4 terms. One of them is just a constant. The other ones involve n. Out of this, the highest term is n cubed. The other ones are lower. And so we would pick the highest term thing. The thing that is important here is the one with the biggest, and so we pick 5n cubed as the thing that we will really care about, and we drop the constant there because we don't care about it, and therefore we could say f of n is equal to order of n cubed. So now we know how to do this. If we get something and we analyzed and we came up with an expression like this, after counting everything else, then we drop everything and then we say this function is order of n cubed. And so its growth rate, it is cubic, is what we are saying. And we can verify this. We can find for the definition that said, what is the C, what's the N0 that would make me say this one I can pick. And so here is an example of what C you could use a C and then so 6. When if you put n0 equal to 10, you can actually verify that this is bounded by 6n cubed for all values n greater than 10. And the reason that you've got a constant or a certain NO that would, for this, it will be true, is to say that we care when the input size grows bigger. So if there is an input size of 9, 8, 7, we don't care. I mean, it's small. And so if it is large enough, then the behavior of this function will be order of n cubed, or it's just n cubed will be a good way to tell it. We can't even tell apart then what constant is, whether it was a 6 or a 7 or 8, won't even matter. Okay, we could also have a bound. Now that I tell you to bound, I'll tell you what sometimes people do a bit lazily. If I say to bound, they can come and give me a very generous bound, right? So if n cubed is a bound, n to the 4th is also a bound, of course. N to the 5th is also a bound, but that will not be very helpful. I never get there. So when it is an upper bound, we try to make it as tight as possible, as close as possible to what it actually would be. And so there is no reason for us to go to this function and call it of order of n to the 4th, because it is so, but n cubed will be a tighter one. But it will not be order of n squared because it is strictly bigger than that. So that's what this, the rest of the story is saying here. Okay, so we just looked at a function that looked like a polynomial. Some terms are added and so on. But our functions can have all kinds of forms. There could be some exponential terms to them and so on. One thing that commonly happens in computer science is things that involve logarithms. And when you look at a book or whatever, what people publish and so on, when you see things that are expressed for running times or similar types of analysis, you never see a base for a logarithm specified. They would not say log to the base 2 or something like that. The reason for it is because of how the big O notation is given. Because it's asymptotic, it actually won't matter. Because if we take logarithms, and if you remember what your basic math knowledge was from high school, you can change bases by just, for example, if I take logarithm of n to the base b, I can have them expressed in the same base by having to write logarithm of n to the base 2 divided by logarithm of b to the base 2. So if you see now how logarithm of n to the base b is and how logarithm of n to the base 2 is, the only thing that has happened there is this expression logarithm of b to the base 2, which is just a constant. The n is not showing up. So that means converting from one log to another log is just a matter of manipulating it and multiplying it by a certain constant. And fortunately, in our big O notation, we don't care about constants, so we can ignore them. So when we see functions, we don't explicitly say what the base is because it is irrelevant. So this f2, this is another example, and this is a little yellow box that you see has got 3n log n to the base 2 plus 5n log n of 2 to the base of log 2 and so on. That is expressed in this way. The bigger term in this case is the first one, the one that involves n and log n to the base 2. And because we don't care about the base, when we write it in terms of big O notation, we just write f2 of n is equal to order of n log n. And so dealing with logarithms in big O notation is a lot of simplification. We don't even need to worry about the base, what base it is used. So the big O notation has a cousin, and it's called small O notation. And this is very rarely used, but it is there in the book, and I want also to tell you. So it's rarely used because we usually would want to say less than or equal to. Just think of the f of n is equal to order of g of n to just mean f of n is less than or equal to g of n. But sometimes that relationship, that inequality could be strict in the sense that it's not equal to, but it is strictly less than, is still when we are thinking in terms of asymptotic functions. When that is the case, and when we want to emphasize that, when we want to say, for example, that f of n is equal to order of n cubed was the example we saw, we also say it's order of n to the fourth. We knew that the order of n to the 4 was a generous upper bound, but when we have even the tighter upper bound we give, but it is strictly less in the sense that we have this definition that you see in front of you now in terms of limits, then we use the small no notation, the small o notation. And so the small o notation says f of n is equal to small o of g of n when this limit goes to 0. And that limit is the ratio between f of n and g of n. So as g of n, as n goes to infinity, this term would go to 0. In other words, f of n is strictly less than order of g of n. And that ratio, because it's strictly less, as n gets bigger and bigger and bigger, goes to 0. So just have this intuitive understanding of to say, f of n is equal to little o of gn, or small o of gn, means f of n is strictly less than c of g of n, whereas f of n is equal to order of g of n would mean f of n is less than or equal to g of n. That will be a nice way to remember. They are rarely used, but sometimes we do have that opportunity to be very precise and be showing that it is exactly small. And so we would say, when f of n is big O, when this one is true, when f of n is small o of g of n, we could safely also say f of n is big O of g of n, right? If a is less than b, I can also say a is less than or equal to b, but I cannot say the other way around. So just a small thing to remember there. So here are some examples, and not one, 5 of them. So you've got f of n on the left and how you might express it as small o of another function there. And it should be obvious. Every single one of them should be obvious why they are the case. But if you wanted to go around and justify with a constant and a g of n that you can demonstrate and want n, so you can say and show the limits and so on, you would see. But every single one of them, replace them to think of it this way. Square root of n is less than n. N is less than n log n. N log n is less than n log n. If you think that way, you will be convinced, and you would not probably need too much of, unless you have all of the time in the world, you don't have to find the C and the thing that would actually verify this one. It should be self-evident. It should be fairly obvious. But small O notations are rarely used. Okay, now we are equipped. Now we know how to analyze. And I will come and get to see what you told me, what the word analysis invokes in your mind. It doesn't have to agree with what I have in mind. No, I didn't even give you. The context I gave you was newspapers and radio hosts and so on, the word analysis. But now we are going to be analyzing an algorithm, and specifically we are going to analyze its time complexity. And so we know how to measure time complexity. We have a tool for doing it. We're going to use big O notation. We are going to now go back and bring up the M1 machine we did for doing the 0 to the k, n to the 1 to the k language that we know was decidable. And so written again, here is what the algorithm or the machine looks like, the Turing machine, the single tape Turing machine looks like. So we know the steps. What we will do now is what I would like you to do every single time you have an algorithm. People write algorithms. Sometimes you don't give yourself enough credit. Maybe you might have come up with a clever algorithm for a problem you were given in class. And usually you don't really come up with a new algorithm. I am kidding. You would probably implement a known algorithm, and you probably implement the algorithm that's not even the best. But you know what I mean. So if you have any day, one time in your future, you design an algorithm, you should take this step to tell somebody else what its time complexity is. You can also, in addition to that, show how it's doing well by running experiments and show you plot results and so on. But this is how you would do your analysis of your algorithm, by looking at the steps it takes, by taking the input size to be n and then counting how many things you do, how many operations you would do. There are certain things that you wouldn't care about, and there are certain things that you would count. So this Turing machine of ours, M1, has got 4 steps or stages. And so we are going to go look at what happens in each of these stages and try to count the operations that happen, to try to analyze its complexity. And by the time we finish all 4 stages, we say we add them up together, and here is what the total runtime for this algorithm would be. And it will be a nice function that we would express in terms of all notations. Okay, we're now in business. Stage 1, scan across the tape and reject if a 0 is found to the right of a 1. I've got the entire tape now, and I'm going to scan it and I'm going to look for things that I could reject if a 0 is found to the right of a 1. So this would take me, look, the tape is going to move all the way on the head, I should say, along the tape, and it's going to finish its job when it has finished reading all of the input, the encoding that it was, and we gave it a name. That length is called n. And so the first stage will take order of n steps to do. It might need to move around, bring back the head to the left and so on. All of that is happening. Notice now, we never cared how many times it has to do scanning of the tape and so on. It will be a constant, and that is now hidden in our big O notation. What is important is how does it grow compared to the size of the input, and that's linear. Order of n is what it takes. We get to stage 2 and 3. And so what's happening in stage 2, stage 3 is indented, if you remember how things were working in this one. So we are going to repeat this if both zeros and remain on the tape. And every time there is something remaining like that, we scan across the tape, crossing off a single 0 and a single 1. And so this, because we are crossing off a single 0 or a single 1, and each time we are doing this, we are going to require half the steps because we are doing one of these two. And so there will be n over 2 steps, but each time we are scanning the whole tape again, and therefore that will be order of n. So n over 2 times order of n will be what is involved in stage 2 and 3. In stage 4, we are going to be looking if there is any remaining 0 or a remaining 1, just to match, pair things up. And if there isn't a mismatch, then we say we reject. If there is a match everywhere, then we say we accept. And that will also be a scan, and that will be a linear in the size of the input. So we now went through stage by stage all of the things that's happening, and we discovered that 1 and 4 are of the same order. They had to involve scanning the tape, whereas stage 2 and 3 had repeated ones, and it was half of the thing that we need in each one of them. And so, and in each one we scanned, so that stage 2 and 3 together was not any longer linear. We had to repeat them, and each time, and this is worst case, by the way, so order of n is what we wrote, so it became order of n squared. Now, we can also, I forgot to tell you, this asymptotic expressions could be used against one another, and so we could actually write them this way. So we have these 3 pieces that we have found out now, and we can add them because that's the total time we need. And so we add them. When we see a term like this, then the thing that will dominate will be the bigger one of these 3, and so this would be order of n squared. This would follow naturally from how we define the big O notations to begin with. So that means when we have looked at the stages in this way, and we look at the stage that is the most expensive, that will be the one that would determine what the complexity of the algorithm would be. Okay, now we can declare victory. We did know how to measure time. We did know how to do analysis. We had a problem, and that problem was to decide 0 to the k, 1 to the k. And we had a Turing machine for doing it, and that Turing machine was M1. And now we know, after we did this analysis, we found out that the total time, the runtime of this algorithm is order of n squared. And that's fantastic. So we did that. Now, what we want to do is, if you remember the overview slide I gave you before, was to measure time. And then now we are going to talk about, just like we said, here is a class of language, they are called decidable. Here is a class of language, they are called undecidable. Here is a class of language, they are called regular. Here is a class of language, they are called whatever they were, these other context-free languages, right? We had classes. Just like that now, if we were to look for algorithms that are decidable, that means they can be solved, and we can have their times analyzed in the fashion I showed you. Can we group them together now to talk about classes? And that is what the subject of classification of language according to time requirements would be. And this one we can do by having to define a class now. And that class is called complexity class. And this is a big term. People who do complexity theory would have complexity classes, and you will be fascinated. We will not go in these courses so much, but there is a whole bunch of interesting classes that what people would come up with. And so the starting point for it is to classify them using this notion called, we will now call the time complexity class called time, with all caps, time Tn, to denote this is a collection of all the languages that are decidable by an order of Tn time. So I'm going to talk about all problems that are linear when T of n is linear. T of n is square, order of n squared, quadratic times, cubic times, and so on. So I can have now this time complexity classes defined using this one to be a collection of languages that are decidable by order of Tn time Turing machine. Okay, now we have that. So now recall this language that we just saw, 0 to the k, 1 to the k, we saw there was a machine for it called M1 that decided it in order of n squared, and therefore it belongs now to this class called time n squared, because it contains all those languages that can be decided by this one. So now we know where this language belongs in this time complexity classes. It belongs to the class that's called time n squared. That means it belongs to quadratic time solvable problems. That's where it belongs. But then we could ask ourselves, and this is what a good computer scientist should ask, can I come up with a machine that decides asymptotically faster? Am I happy with the quadratic time? This is where most of the things that we do in research or in everything that we do most of the time comes down to, because having to solve a problem is not enough. You will always want to have the fastest possible algorithm. And now I'm talking about asymptotically faster, not the way you optimize your code and you tweak your things and you say, and I have this, modification to my code and so on and make it run faster. Of course it will run faster. You have, optimized your code. That's not what I mean. What I mean is asymptotically faster. It doesn't have to, I don't even need to see an implementation for it. Is it better than n squared? That question for computable problems is always an interesting one. Sometimes we have problems that have multiple ways to solve them and we care for the faster one. Sometimes we don't really have too many options and then we live with the one that are, even though it is not fast. Okay, so we do have, for this particular language, we actually do have a faster algorithm. And so I'm going to present M2. M1 was the one that was doing a lazy job. Now we've got a clever algorithm. When I describe this one, go back in your mind and try to remember the sorting algorithms you've learned. Some of you might have taken a data structure. I'm sure most of you have, but some of you might not have. If you have seen sorting algorithms of all kinds. We start with the thing that's maybe the thing that would come to your mind, and then you get more and more clever, and so you'd get to reduce the runtime of that algorithm by getting to be clever with it. So if you know, then relate it. If not, then don't worry too much about it. But here we have an algorithm that was trying to decide 0 to the k, 1 to the k, but it is doing to go faster one. And so there is a fundamentally different way we want to think about it, rather than tweaking to get some speed ups in some of the states. Rather, we would have different strategy. And so this is strategy. I think we might have seen this, but I'm not so sure. But I think we probably have seen this Turing machine for deciding that language. And it has to do by being clever, instead of having to do the tape and match up zeros and ones, by having to do this that would reduce the size by half every time. And so that's what's happening here. So in stage one, we scan across the tape and reject if a zero is found to the right of one. That's similar. What is happening in stage 2 to 4 in the current one is different from what was before. And this one would go by having to repeat as long as some zeros and ones remain on tape. But instead of just one step there, now we've got 2, 3, and 4. And so we scan across the tape, checking whether the total number of zeros and ones remain is even or odd. And if it is odd, then we know they're not going to pair up. And so there is no business checking them, crossing off and things like that. We can immediately go and reject. But if it is even, then there is something to do. And because it is even, now we can get crossing off every other rather than every element that we did in the previous algorithm. That means if you boil this thing down now, you would cut on how much operation you needed. And that would show very nicely in your analysis. And that step where things are being reduced comes in stage 2, 3, and 4. So in each one of them, there is a scanning that's to be done. And so that remains order of n. But how many repetitions you would do is reduced. Before, it was just n over 2 and basically the same magnitude n, but now because we reduce it by half every time, the first time we just have to invest that initial investment, but every other thing will be reduced half, 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 and then we will end when the input size is finished, and that will take only logarithmic steps. You know, when something is half, 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 you could find the height of that one, it would be log of n. And therefore, stage 2, 3 together, 2, 3, 4 together would be order of n times log n instead of order of n squared. And so when we add up these 3, there is a term that's order of n log n that is dominant, and so the algorithm is now faster. What we had in algorithm M1 was order of n squared. This one is n log n, which is faster. Think sorting. you probably would immediately relate what an n-squared algorithm would be and what an n log n algorithm would be. Okay, now we saw a problem, we saw a language. M1 implied that this language is in time n squared. Yes. M2 implied that this language is in time n log n. So what are we going to say about A? Which one does it belong to? In fact, the second result, this one about n log n, cannot be improved any further. And this is one of the happy places where you can show impossibility results. Don't blame me if you could get any clever you want. As long as you have a single tape machine, you would never be able to do this thing in faster than n log n time. That would be something that people can prove and people have proved. And that result actually is true of regular language in general. In case you haven't recalled the 0 to the n, k, 1 to the k, and it's being regular, this is a statement that's true of regular language. You cannot do any further if your machine is going to be a single tape. However, this language could be decided even faster if our Turing machine is equipped now with a second tape. And there is a description of an algorithm that does that in the book. It's not too important, but you're getting help. So you've got a place to save. So you've got an extra room. So if somebody asked you to swap things around and so on and say, do it in place right here, you would say, well, I can't do it unless I wait this long and I'm moving things. But if somebody gives you another room to put things temporarily, then you could do things faster because now you've got an extra room. That's basically what happens. And so you get now to run this one in linear time, which means now the complexity of A on a single tape machine is order of n log n. I can't do it any faster. But if I get a 2-tape machine, it becomes linear order of n. So that means the complexity of this language now has depended on the model of computation selected. And that brings me to my last slide, which is a perfect timing, and to talk about the distinction between complexity theory, which is what we're being introduced to now, and computability theory, which is what we did the last 4 or so weeks, 4+ weeks, since we started after spring break. And so this discussion highlighted an important difference between complexity theory and computability theory. In computability theory, the Church-Turing thesis and all the variations of the Turing machines we saw never mattered in terms of adding power to classes of languages. And so it was the same. In fact, Turing machines was equivalent to lambda calculus. That's what the Church-Turing thesis was also saying. So that means there was computability theory that was kind of not sensitive to these models that we are using. It was telling us the same thing, which was a good thing. In complexity theory, the choice of a model affects the time complexity of the language. And so we classify, this is a big distinction, an important distinction to note. In complexity theory, what we classify computational problems, because they're all decidable, is according to their time complexity. But then if we have different models and we've got different complexity to measure with them, which one are we going to use to talk about them? And that seems like a little bit hopeless, because now we could have many models and we've got different complexities and we just kind of become in a difficult situation to talk about them in general terms. That would have been unfortunate. But there is a fortunate thing we have, and that is because time requirements don't actually vary so very much when we have deterministic models. And you saw the time Tn, that was the complexity class, linear, n log n, n squared, and so on. We could build our tents large enough. That was my way of putting it. That's why I put it in quotation marks. If we build our tents large enough, then we could say these are all the same. We don't really care that much. So we put them in one big tent and we have them one class now. And then there will be others who would not say that tent is not big enough for me, and so I won't live there. That will be the subject we will handle next time. And so complexity theory has got ways, definitions that are sensitive to the choice of a computation model, but we have a way to get around that so that we become insensitive to those small variations because they don't matter much, and still now talk about problems that we can in a practical way solve. They are tractable, and others that are not. And that will be what I will introduce on Friday. All right, anybody has got any questions for me? I'm going to tally what you told me about your analysis answer, but I hope this was clear. Was this okay to follow along? Okay, can we do it in order of time if we have empty? That was a very good question. I would argue that you could probably, but I'm not sure if there is a practical meaning to that. But I think that's a very interesting question. And my first feeling would be theoretically yes, but I'm not sure if there is any meaningful thing to talk about that. Well, we would have, and I will have to take back, maybe we'll build up on it on Friday. We need to read the input. And so there's a growing body of work that's going on now that's called sublinear algorithms. That means you would not even need to read the whole input to talk about it. But generally speaking, if I want to do something with my input, I have to at least to read it. So sublinear algorithms in the kind of models that we talk about now don't make sense. So you will need to have the tape to read your input. At least I need that much, and that would mean immediately order of n. But the question was very interesting. Okay. Okay. If you do not have any further questions, then I will say we are done for today, and I'll see you on Friday, and take care of yourselves, all right? Bye.